Hello, everyone. Today we're diving into a fascinating topic in engineering mechanics, the kinematics of rigid bodies. This fundamental concept forms the backbone of how we analyze and understand the motion of solid objects in engineering applications. In this introductory slide, let's understand what makes kinematics of rigid bodies special. Unlike particle motion, which we've studied before, rigid body motion is more complex because we're dealing with objects that maintain fixed distances between their points. Think of it like a ruler moving through space. Whether you're spinning it or sliding it, the distance between any 2 points on that ruler never changes. This fundamental principle is what makes rigid body motion unique and interesting to study. Now let's delve into what exactly we mean by a rigid body. In engineering, we treat rigid bodies as idealized objects where deformation is practically non-existent under applied forces. Imagine a steel beam. While in reality it might bend slightly under load, we often analyze it as a perfectly rigid body to simplify our calculations. The key assumptions we make are that the body doesn't deform, stretch, or compress, and both rotational and translational motions can occur simultaneously. Common examples include rotating wheels, sliding doors, and mechanical components like gears and pulleys. Let's begin exploring the first type of rigid body motion, translation. In pure translation, every point on the body moves along parallel paths with identical velocity and direction. Think of an elevator moving up and down. Every point on the elevator travels the same distance in the same direction. We categorize this into two types: rectilinear translation, where points move in straight parallel lines, like a car on a straight road, and curvilinear translation, where points follow curved but parallel paths, like a car on a curved road. Moving on to rotational motion, this is where things get interesting. In pure rotation, every point on the rigid body moves in a circular path around a fixed axis. We measure this motion using two important quantities: angular velocity, omega, which tells us how fast the rotation is occurring, and angular acceleration, alpha, which indicates how quickly the angular velocity is changing. A fascinating aspect is that while every point has a different linear velocity, v equals r omega, they all share the same angular velocity. Think of a spinning fan. The tip moves faster than points near the center, but they all complete one rotation in the same time. Here we encounter the most common type of rigid body motion in real-world applications: general plane motion. This combines both translation and rotation, creating complex trajectories for each point on the body. The perfect example is a rolling wheel. It's simultaneously rotating about its axis while translating forward. This combination creates fascinating patterns of motion that we'll analyze in more detail later. In this slide, we're introduced to absolute motion, which analyzes rigid body movement relative to a fixed reference frame. We use two primary coordinate systems: rectangular coordinates, x, y, z, for translational motion, and polar coordinates, r, theta, for rotational motion. These systems help us break down complex motions into manageable components for analysis. Think of it as having different tools in our toolbox, each suited for specific types of motion analysis. This slide presents fundamental equations that govern rigid body motion. These mathematical relationships help us quantify and predict how rigid bodies move under various conditions. While the equations might look complex, they're essentially describing relationships between position, velocity, and acceleration in both linear and angular terms. We'll use these equations as building blocks for solving more complex problems. Let's discuss the concept of relative velocity. Relative velocity is the vector difference between the velocities of two bodies. It helps us understand how fast one object is moving compared to another. The formula for relative velocity is velocity of a relative to b equals the velocity of a minus the velocity of v. This concept is essential in many fields, such as navigation, where it helps determine the speed and direction of a moving object concerning another. In this continuation of relative velocity, we dive deeper into practical applications. Using the example provided, when two cars move in the same direction at different speeds, 30 meters per second and 20 meters per second, their relative velocity is simply the difference, 10 meters per second. This concept is crucial in many real-world applications, from aircraft navigation to collision avoidance systems. The physical interpretation helps us understand how objects interact when moving relative to each other. Let's explore how acceleration works between moving bodies. Relative acceleration is a crucial concept that builds upon our understanding of relative velocity. When we analyze how objects accelerate in relation to each other, we need to consider both their individual accelerations and how they interact. This becomes especially important in engineering scenarios where we need to understand how different parts of a machine influence each other's motion. The mathematical relationships shown help us quantify these complex interactions in a systematic way. In this continued discussion of relative acceleration, we focus on practical applications. Two key areas where this concept shines are motion analysis and engineering design. When we're analyzing how machine parts interact, understanding relative acceleration helps us predict wear patterns, optimize performance, and ensure smooth operation. For instance, when designing a robotic arm, we need to account for how the acceleration of each joint affects the others to achieve precise control and prevent unwanted vibrations. Let's discuss the instantaneous center of zero velocity, ICZV. The ICZV is a point in a rigid body or system that is momentarily at rest relative to an inertial frame. This concept simplifies the analysis of rigid body motion, especially rotational motion. Key features include that all points on a rigid body move as if they were rotating around the ICZV, and the velocity of the ICZV is zero at a specific instant. To find the ICZV, identify 2 points on the rigid body with known velocities. Draw velocity vectors perpendicular to the lines joining these points. The intersection of these perpendicular lines is the ICZV. Building on our understanding of ICZV, let's look at some practical applications. A perfect example is a wheel rolling without slipping. The point where the wheel touches the ground is momentarily at rest. That's our ICZV. From this point, we can determine velocities at any other point on the wheel. For instance, if the wheel's center moves at velocity v, the top of the wheel moves at 2v, while the bottom point, our ICZV, has zero velocity. This concept is invaluable in analyzing mechanisms and linkages in machinery. In this slide, we explore how velocity behaves in rigid body motion. The relationships shown help us understand how different points on a rigid body move relative to each other. When we combine translational and rotational motion, each point on the body has its own unique velocity, yet all these velocities are related through the body's rigid nature. Understanding these relationships is crucial for analyzing everything from simple rotating shafts to complex mechanical systems. Here we examine acceleration in rigid body motion, which adds another layer of complexity to our analysis. When a rigid body undergoes both rotation and translation, we must consider both linear and angular acceleration components. The equations shown help us break down these complex motions into manageable parts. This understanding is essential for designing systems that need to start, stop, or change directions smoothly and safely. Now we're seeing how all these concepts come together in real-world applications. First, We look at relative velocity in machines, particularly in gear trains and cam mechanisms. These systems rely on precise velocity relationships to function properly. Next, we see how ICZV simplifies calculations in linkages and robotic arms. Finally, we explore how relative acceleration analysis ensures dynamic stability in vehicles and machinery. These applications demonstrate why understanding rigid body kinematics is crucial for engineering design. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.